The universe is vast, and our cosmic address is just one small corner of it. Here on Earth, life flourishes in every imaginable niche, from the deepest oceans to the highest mountains. But how did it all begin? This is one of the greatest detective stories ever told. We're searching for clues, not to a crime, but to our own origin story. Finding the very first evidence of life on our planet is more than just a scientific curiosity. It's about understanding our place in the cosmos. Every tiny fossil, every chemical trace, pushes back the timeline of existence and expands our imagination about what is possible. It tells us that life might be more resilient, more ancient, and perhaps more common than we ever dared to dream. This quest takes us to the most ancient rocks on our planet, remnants of a world that was barely recognizable. Imagine a young Earth, a turbulent volcanic sphere bombarded by asteroids, with boiling oceans and a toxic atmosphere. It seems like the last place you would expect to find life. Yet, it is in these hostile, primordial landscapes that scientists are finding tantalizing hints. These clues are not giant dinosaur bones, but microscopic filaments, unusual chemical signatures, and layered rock formations. Each discovery is a breadcrumb leading us further back in time, closer to the moment when non-living chemistry sparked into biology. The search is a profound journey into the deep past. The excitement of this search extends far beyond our own world. If life could take hold on Earth so early in its chaotic history, what does that mean for other planets? Could life have emerged on Mars, or on a moon orbiting Jupiter, or Saturn? The search for Earth's earliest life is fundamentally connected to the search for extraterrestrial life. The principles are the same. We are looking for the fingerprints that biology leaves behind, whether here at home or on a distant world. Each fossil candidate, no matter how controversial, teaches us what to look for and sharpens our tools for the grand exploration that lies ahead. It's a story that connects us all to the stars. The evidence we find is often ambiguous, sparking intense debates among scientists. Is that tiny swirl in the rock a fossilized microbe, or just a trick of geology? Is that chemical signature a sign of photosynthesis, or the result of immense heat and pressure over billions of years? This scientific argument is not a sign of failure. It is the very heart of the process. It forces us to question our assumptions, refine our methods, and be rigorously honest about what we know and what we don't. Each piece of evidence is scrutinized, debated, and tested. This is how we edge closer to the truth, one microscopic fossil at a time, on our grand journey to understand life's dawn. Our first stop is in Quebec, Canada, in a band of ancient rock called the Nouveau-Guétook Greenstone Belt. Here, scientists found something extraordinary inside rocks that are an astonishing 4.28 billion years old. At that time, Earth was just a baby, a mere 200 million years after it formed. The discovery? Microscopic tubes and filaments made of an iron oxide called hematite. What's so exciting is that these tiny structures look almost identical to the shapes made by modern iron-eating bacteria living near deep-sea hydrothermal vents. These vents are like underwater volcanic chimneys, places teeming with life that thrives on chemical energy instead of sunlight. This find could be our oldest ancestor. The implications are staggering. If these are truly fossils, it means life appeared on Earth almost instantly after the planet's surface cooled enough for liquid water to exist. It suggests that the leap from non-life to life might not be so difficult after all. But here comes the great scientific debate. Could these beautiful, lifelike structures be nothing more than a geological illusion? Some scientists argue that similar shapes can be formed through non-biological processes, as minerals crystallize out of hot, chemical-rich water. The question remains, are we looking at the dawn of biology, or just a fascinating example of complex mineralogy that happens to mimic it? The jury is still out. Now let's travel to Aquileia Island, off the coast of Greenland. The rocks here are also among the oldest on Earth, dating back over 3.8 billion years. Inside these heavily processed rocks, scientists found tiny specks of graphite, which is a form of pure carbon. When they analyzed this carbon, they discovered a peculiar chemical signature. It contained a higher ratio of a lighter type of carbon, called carbon-12, compared to its heavier cousin, carbon-13. On modern Earth, this specific carbon signature is almost exclusively the work of living organisms. Plants and algae, through photosynthesis, prefer to use the lighter carbon-12, leaving this distinct fingerprint in their remains. This chemical whisper from the past could be evidence of photosynthetic life existing hundreds of millions of years earlier than we previously thought. Imagine tiny, primitive organisms harnessing the sun's energy when our planet was still young and violent. However, like our Canadian fossils, this evidence comes with a big question mark. The rocks on Aquileia Island have been cooked and squeezed under immense heat and pressure over billions of years. Critics suggest that these intense geological processes could have altered the carbon, creating a false biological signal. It's possible that we are seeing a ghost in the machine, a chemical echo created by geology, not biology. Our journey now takes us to the Pilbara region of Western Australia, a hot, dry landscape that holds some of the best preserved ancient rocks on the planet. Here we find incredible structures called stromatolites in the 3.4 billion-year-old Strelley Pool Formation. Stromatolites are layered, dome-like mounds that look like rocky cabbages. Today, they are built by colonies of microbes, typically cyanobacteria, living in shallow water. The microbes form sticky mats that trap tiny particles of sediment. As they grow upwards towards the sun, they create new layers, building these structures over thousands of years. For decades, these were considered the gold standard for early life. For a long time, the Strelley Pool stromatolites were celebrated as definitive proof of complex microbial communities thriving in the Archean eon. They seem to be the handiwork of ancient architects, building entire ecosystems layer by layer. They told a story of a sunlit, shallow-water world already bustling with life. But science is always questioning. Some researchers now propose that these specific ancient stromatolites might have formed without any help from life at all. They argue that the simple, even layering could be the result of mineral crystals precipitating out of salty water, creating a structure that just happens to look like a biologically formed one. The debate challenges us to define what makes a fossil a fossil. Let's stay in the ancient past, but look even closer, at a microscopic scale. In 3.5 billion-year-old rocks from both South Africa and Australia, scientists discovered tiny, spherical objects named eosphera. Under a microscope, these microstructures are truly stunning. They look remarkably like modern single-celled organisms. Some appear to have distinct cell walls, and a few even seem to contain internal structures, almost like a nucleus. Most excitingly, some of these tiny spheres were found in pairs and groups, suggesting they might have been caught in the act of cell division, the fundamental process of life. It was a breathtaking discovery, seemingly showing complex cells from the dawn of time. Initially, these microfossils were hailed as slam-dunk evidence for cellular life in the Archean. They were so convincing, so lifelike. But as our understanding of geology has grown, so has our skepticism. Geologists have proposed an alternative, non-biological explanation. They suggest these spheres could be mineral artifacts. Imagine tiny bubbles of silica or carbon-rich fluids trapped in cooling rock. Under immense pressure over billions of years, these bubbles could solidify into spherical shapes that perfectly mimic cells. Once again, we are faced with the ultimate question. Are we looking at our ancient microbial ancestors, or just a beautiful, coincidental trick of the light played by minerals? Our final clue in the story of early life isn't from Earth at all. It comes from our neighbor Mars. For years, orbiting satellites and rovers like Curiosity have detected plumes of methane gas in the thin Martian atmosphere. On our planet, over 90% of the methane in the air is produced by living things, from microbes in swamps to cows in fields. Methane is a fragile molecule. It's destroyed by sunlight in just a few hundred years. So, if we keep detecting it on Mars, it means something there is actively producing it right now. It is a modern-day chemical signal that demands an explanation. This recurring puff of methane is one of the most exciting signs in our search for extraterrestrial life. One tantalizing possibility is that microbial life, let's call them methanogens, could be alive and well beneath the Martian surface. They could be thriving in pockets of liquid water, sheltered from the harsh radiation on the surface, quietly burping out methane gas that seeps into the atmosphere. Finding life on Mars, even simple microbial life, would change everything. It would mean that the spark of life occurred at least twice in our own solar system. It would suggest that the universe could be teeming with life. We would finally know that we are not alone. But before we celebrate, we must consider the alternative. There is a known geological process that can also produce methane, and it doesn't require life at all. This process is called serpentinization. It happens when water interacts with certain types of iron-rich rock. creating a chemical reaction that releases methane as a byproduct. This process is known to occur on Earth and could very well be happening on Mars today. The methane plumes could be nothing more than the planet's sterile geology, letting off a bit of gas. The signal is ambiguous, a ghost that could be biological or geological. These 5 great mysteries, from the ancient rocks of Earth to the thin air of Mars, teach us a profound lesson. The line between life and non-life can be incredibly blurry. Nature is full of complex patterns, and geology can sometimes be a masterful mimic, creating structures and chemicals that look just like the handiwork of biology. This uncertainty doesn't diminish the quest, it makes it more thrilling. It forces us to ask bigger questions. What is life really? And what are its fundamental signatures? The search for our origins is far from over. We have so much more to learn, and the cosmos is waiting.